Hello and welcome. In this video, we're going to look at how to calculate series RLC current in terms of time. So this is kind of going to apply all of our understanding of Ohm's law, series circuits, voltage drops to this circuit to be able to work through all of these here. So they gave us voltage in terms of time across C1 capacitor, VC1 of T. That's this over here, VC1 of T. Right, and that's this 6e to the negative 250t. And that t is our factor. And so remember, we're working with a sine wave here most of the time. And so we could have a t factor up here that's going to give us a very specific voltage over here. Or we can have a t factor that's way down here. And that's going to give us a different voltage. Right? It's going to be different on our scale of voltage. And so we want to be able to track that. And so to do that, we just set it in terms of time. And we know that if our voltage is on the rise, then our current is also on the rise. And if our voltage is on the fall, then our current is also on the fall. They're going to follow each other. Right? So that gives us that idea that a higher voltage gives us a higher current. And so then the only other thing that we need to keep in mind is that we're working with a series circuit. So that series circuit, once we find the current through C1, that's the current through all of the circuit, right? Because there's only one current in series. And so that's what our goal is. We're going to find the current through C1. We're going to use that to find the voltage drop across the inductor and then across the resistor, right? Using that IC1 in terms of time, because that's technically our I total. All right, so that is our path. So our first step is to apply IC1 in terms of time, which gives us this little equation down here. So we'll start off with that. We'll say that the current through the C1 capacitor in terms of time is equal to C1, our capacitor value, which we're given 0.2 microfarads. Then they give us this d over dt, so we'll write that in, d over dt, and this little v is on top. I usually write that at the end over here. That way it's easier for it to be separated out. The d over dt is going to cancel completely out, and we'll just be left with multiplying by our v. And they tell us to use the voltage that's given, and so that's going to be the voltage drop across our C1 capacitor. So I'll put in 6e to the negative 250t, and that is a voltage value. So this is the equation that we are going to solve down. We're not going to be able to completely eliminate it because we don't know what time is. They didn't give us a time value. They want us to keep it in terms of time. And so we just need to reduce this. And to do that, we just get rid of this derivative here and solve it out, right? And so this derivative, these ones are really tricky to get the hang of at first, but this derivative basically tells me to pull this number out front and pull this number out front and then leave whatever is on the tail here. And so let's write that out, because now we have IC1 of t is equal to 0.2 microfarads multiplied by, because we pulled the 6 out, 6 multiplied by our exponent up here, which is negative 250. And then whatever was left in there is going to stay. We eliminate all the constants at that point. And so we're basically left with e to the negative 250 t, and then this is going to be whatever we multiply out. So in this case, our answer is going to be in milliamps or microamps. But we don't know that yet. We only know that because it's written down here as our answer. So the trickiest part here is what to leave where. And so you pull out your exponent number, but you also leave it. Oops, I missed the 0 here. But you also leave it in the end here. And so that's the important part, which we give you that down here. It shows it down here. And so we just need to reduce out the front half of this. So we'll multiply 0.2 by 6 by 250, and we'll end up with some kind of microamps output. Since we're multiplying these across, we can ignore this microamps and know that we're going to end up in microamps. Let's do that. We'll say 0.2 microamps multiplied by 6 multiplied by negative 250. And that gets us a negative answer of 300 microamps. And so that is our first number down here. So we know that our IT, or the current through the C1 capacitor, is 300 microamps. So we can type that into our bottom thing here, 300. And we'll actually scroll down a little bit. So let me erase some of these here and we can scroll down to see the other ones that they want us to solve for. Because we're going to use this value here in the rest of them. So down here it says that they want the voltage across the L1 inductor. We'll look at that. That's this bottom one down here. And then they want us to know the voltage drop across the R1 resistor also. Erase a few more. So we got 300 microamps as our answer. It's 300 times 10 e to the negative 250 t is the final answer for that. So we're going to use that whole thing in our next one, which is right here. They give it to us. Let me get a different color here. So with this one, they give us the voltage across the L1 inductor in terms of time is equal to L1, which we know it's given in the picture there, 8.2 millihenries. And then we do a d over dt, so we'll write that in, d over dt. I like to keep that all compact with it. And then I just look at what is paired with that, and it is the IC1 of t. It's our first answer, IC1 of t. So we're going to put our first answer in after this. I'll even write it in red so we can spot it later. So IC1 of t is negative 300 e to the negative 250 t microamps. I just want to make sure I put a negative in front of this. Did not. So put a negative in front of my current there. Make sure you don't drop your negative off of that. Okay, so now we just need to reduce this out here, same way we did before. We'll pull out our constant and our exponent, and that will allow us to reduce that derivative out of there completely. So we want to get rid of this guy by pulling this one out front and this one out front also. So we'll rewrite this. VL1 of t is equal to 8.2 millihenries multiplied by negative 300 multiplied by negative 250. And then at the end here, we'll just have E negative 250 ET microamps. And in this case, we're going to convert this over. We're going to end up with microvolts at the end. So we leave it in volts if we want to. And that is what they got right here. So that's the ending that they wanted us to aim at. So now we just need to reduce the front half. We'll take that down and say that we're going to multiply these three numbers together. Send that out. If we leave it in microamps, we get microvolts. So 8.2 is milli, right? So we got to watch out for that. We want it in microvolts, so we can reduce this down to microvolts and take this 8.2 mH and say we need to go back by 8 more, or by 3 more, because we're at negative 3 right here. We need negative 6. So 1, 2, 3 would put us at negative 6. We'll plug in these zeros and we'll put a micro at the end. So we'll type in 8,200 to get that into micro. And then we'll multiply negative 300 and we'll multiply negative 250. That doesn't seem right. We'll plug in the full thing here. So let's write in, we'll say 8.2 millihenries. We want to move that into range. And so we'll say 0.0082 multiplied by negative 300 multiplied by negative 250. So, oh, hold it. If we put all of these into micro here, we've got 8200, and then this one is already in microamps here. We got to make sure we account for that microamps while we plug this in here. So 8200, that's that millihenries in micro. We'll multiply that by -300, again, milli to micro, and then we'll multiply that by 250. So we want to plug these in fully. We have millihenries and microamps that we need to use here. And so we'll say that we have 0.0082. That's our millihenries. We'll multiply that by -300 times 10 to the negative micro with -6 here. And then we'll multiply that by 250, -250. And that gives us this small little number. It's 6.15 times 10 to the -4. That's not in notation, so we'll move that into notation and say that our voltage, L1, in terms of T is equal to, we'll move it into micro, so that means it's -4. We got to go up to -6. We'll move it to the right by 2, and we'll get 615 microvolts. And then that has that ending on it, E -250 T, but they already have that written in here for us, so we'll just type in our magnitude of 615. Okay, and so now we're on to the last stage, which is just our resistor. We know that our current value is the same for all of them, so -300 microamps is our current value. We'll multiply that by our resistance of that, and then we'll get a millivolt value out for it. That shouldn't be too bad. So we'll take our resistance. It's a linear resistance, so 2700 multiplied by our -300 times 10 to the -6. And that gets us -0.81. That is negative for each of these, so make sure you plug in your negative at the beginning. Don't miss your negative. The inductor voltage was the only one that isn't negative because it has 2 double negatives in it. This one should be negative because we're only multiplying one across. So this is a negative. We want to put it in millivolts. We got to move this over to 810 to get that into millivolts. All right, let's check our answer. Here we go. Okay, let us know if you have any questions.